In the previous video, we talked about projection onto a general subspace of m dimension. So we have m linearly independent vectors, and onto which we took the projection of a vector. Now we are going to see the orthogonal factorization of a matrix, which we call as Gram-Schimdt factorization. The objective of this particular factorization is to make one of the factor as a orthogonal matrix, so that q transpose q is I. So let us suppose if the factorization does E is equals to qr, then r's value, so q is the orthonormal matrix, and if you multiply the whole thing by q transpose, you will get a simple and elegant solution for r. So now the idea is to how to create is as follows. Now what we will do, this will be our algorithm. First vector we will choose as it is, the same vector. The second vector will be q2 dash, and we will take the second column vector from that matrix, and we will subtract any projection onto the previous, that is A1 subspace. So the projection of A2 along the subspaces generated by the previous vectors is subtracted. So that Q2 has only that portion which is not yet covered, only that particular part which is not yet seen. So in Q3 dash, we further go for only for that part of A3 which is not yet covered through the previous vectors, and that's how we will go about it. Once we are done with this, once we are done finding these orthogonal vectors, then we will subtract, or then we will normalize all these vectors, and this will make the matrix made up of q1 q2 qn to be orthogonal matrix, the orthonormal matrix. Now one very specific property of orthogonal complement is that if you want to take the projection of any vector AR generated by a space this, then it is equal to the summation of projection along the each orthogonal vector. So instead of taking the projection onto non-orthogonal vectors, if we take the projection over the orthogonal vectors, then the direct sum of the projections will give you the vector, right? So instead of taking the projection along the subspace generated by this, we can find out the projection, just projection matrix for each of the previously generated vector q1, q2, q3, and so on and so forth. So let us see how after that how it goes. So before going into that, let us try to prove that what we mean, that the projection, if taken on the orthogonal basis, if you take the projection on the orthogonal basis, then the projection is equals to the projection along one basis vector plus projection along another basis vector. So let's just try to see it. Let us suppose we have a subspace spanned by these two b1 and b2 vectors, and both of them are orthogonal, right? Now we want to prove that the projection along this subspace generated by b1 and b2, so uh, the projection along that, or the error in the original vector, the deviation from the original vector from the projection, is exactly same as that of the projection or the error between the the actual vector and the projections uh, generated individually over the basis vectors. Okay, so let us see how it goes. So here we have the projection matrix or the projection function. Now the projection function, with the formula you can expand it like this way, right? If you further try to simplify, you will find that you will reach here. But since b1 and b2 are orthogonal, so this comes out to be 0, right? This comes out to be 0. So ultimately what will happen, we get this way, and finally we get this formula, which means that the projection along the subspace b1 b2 is equals to the projection sum of the individual projections taken individually on every basis vector, if the basis vectors are orthogonal. So using this particular property, we can find out the projection. We can simplify these things. This part, we can simplify this part just by taking the projection on orthogonal basis vectors generated by the of the space generated by a1 and a2. So a1 and a2 is generated subspace. Now instead of a1 a2 as linearly independent vectors as the basis, we will take orthogonal basis vectors. And if we take orthogonal basis vectors, so instead of taking the projection along a1 and a2, we will take projection along a1 first and then projection along a2, and then subtracted both the things to get the thing done. Okay, and that is the refined algorithm now. So the new algorithm becomes this one. You take the first vector to be same, the second vector you take and you subtract the projection along the previous direction. So we, at any stage now, we are going to subtract the projection along the previously found orthogonal vectors. By subtracting this, we are getting the orthogonal complement of the vector, and this way we are actually saving a lot of time. Now just for an example, here is a quick look of the QR factorization. So let us suppose that this is the matrix. So the first vector can be taken to be this, and the second vector is the vector, this one, minus the projection along this vector, right? And the next one is the third vector, 3 to 1. Okay, 3 to 1 minus projection along the previously found two vectors. previously found two vectors. You can see like here. So previously found two vectors. So we subtracted the projection along previously found two vectors. And finally, we come up with this thing. Now you can check q1 dash is orthogonal to q2 dash. So you can find out that these are orthogonal to each other. Then we finally normalize them, and once we normalize them, we get a q. And after finding q, you need to find r, which is nothing but q transpose a. So which can be done, right? Now there is a question that, okay, that's fine. Now we can factorize the things. There is another thing. There is a small thing that we can also see how to take the projection into the affine space, onto affine space. So to take the projection onto affine space, there is nothing big. You just take the subspace, the affine space, the corresponding subspace you find. Once you find the corresponding subspace, take the projection as we have done previously. Take the projection there, and then add the support point, and that will do our job. The rest you can see from the chapter 3 of MML book to clarify more on this particular idea. Thank you for the video. In the next video, we will be going to see more on determinants.